So, hello everyone, and welcome to our digital days. My name is Markus Eberle, and I will moderate this webinar and this presentation today. We are very pleased that you took your time to participate in our virtual conference. Yeah, the topic of today's presentation is why, what, and how. A beginner's guide to crystals and oscillators. Our speakers today are Pavey and Malcolm Lennox, who are working at Würth Elektronik, IQD, as technical support engineer and account manager. They will hold today's presentation and also answer your questions later on. So before we start the presentation, I would like to point out one thing. You will be muted during the presentation. That means that you cannot ask us questions via your microphone. But nevertheless, you can ask us the questions with the chat function, or it's called questions. So you can find that in the webinar control panel. The presentation will be about 30 minutes long. After that, we have scheduled 5 to 10 minutes for your questions, and we will go into a little Q&A session with you. If we can't answer all your questions within this time, we will answer them via email afterwards. And if you still have any other questions left after the webinar and the presentation, you can also just email us at exhibition@we-online.com. At the end of the presentation, you will be asked to participate in a feedback survey. Of course, we would be pleased if you take your time and fill out the survey and help us to improve our event. You will also receive the link to the presentation you will see in the next few days. And also the recording will be available at our website shortly. So now I will hand over to our speakers and I wish you an exciting presentation. Have fun.
Thank you for joining us today, and a big welcome from here in Crewkerne, Somerset in England. My name is Malcolm Lennox. I'm an account manager here at IQD Frequency Products. I'm joined today with Chris Pavey, one of our application engineers here at IQD. I started work for IQD back in the summer of 2021. I come from a completely different background, so it's been a big learning curve, and I've had a lot of questions, and I must apologise to the applications team and thank them for their patience. I still have a lot of questions. I've still got a lot to learn. So Chris and I have put together the following presentation and some of the questions I've had over the first 6 months I've been here at IQD, and I hope you find this helpful. So I quite often think the men and women in history who make discoveries that we take for granted in the modern world are taken for granted. So my first question is, what is the history of using crystals for frequency products?
So, in 1880, Jacques and Pierre Curie first noticed and investigated the piezoelectric effect in quartz. And as you can see from this timeline, further studies were made into using quartz as a frequency device. But it wasn't until 1924, when George W. Pierce first applied for a patent for an electrical system for a self-sustaining oscillator that we know today as a Pierce oscillator. And in 1927, the first quartz crystal oscillator standard was developed by Warren Marrison of Bell Laboratories.
So probably the first fundamental question I had was, why do crystals vibrate?
Quartz crystals, or the crystalline form of silicon dioxide, is among a group of materials known as a piezoelectric type material. Other materials include lithium niobate and gallium phosphate. Due to the specific crystalline structure of these materials, when mechanical stresses are applied, a voltage is generated. Transversely, if a voltage is applied across the material, it will create stresses across one or more different planes. If we took the voltage produced by stressing the material and fed this back into the material itself, it would cause the material to deform again, thus producing a voltage. And this process would repeat at a specific frequency and we call this the resonance frequency of the material. But this repetition would die away quickly due to losses in the system. If, however, this voltage were fed back into the input of an operational amplifier and a proportion of the output connected to the other side of the crystal, the effect would be a self-perpetuating sine wave, and this is the basic working principle of a modern Pierce oscillator circuit.
So on a little bit of research when I first started, it seems there's over 2 billion quartz crystals produced each year, which is amazing. How do we produce this number as an industry?
Crystals occur naturally in nature. Natural crystals can be excavated and used in an electronic circuit, but since the 1950s, synthetically grown crystals have become widely available. The process used is a solution growth technique called hydrothermal growth. Hydrothermal growth is conducted in a steel pressure vessel called an autoclave. A supply of nutrient material, usually natural clear or milky quartz, is placed at the bottom half of the autoclave, and in the top half, seed crystals cut from either synthetic or natural crystals are hung. The temperature difference between the growing and the dissolving chamber is the chief process in control of the growth rate. The temperature difference controls not only the supersaturation in the growth chamber, but together with a baffle, controls the rate of fluid and heat transfer between the two chambers. Growing temperature also has a strong effect, with the growth rates increasing and decreasing with temperature. After sealing the vessel, the autoclave is heated to operating conditions with the use of external heaters. Typical operating conditions are generally between 300 and 400 degrees C, and the internal pressure developed is controlled by the temperature and the amount of solution added to the autoclave, and is typically between 1000 and 1500 bar. Using this method, growth rates of up to 1 millimeter per day can be achieved.
With such a latitude of different sizes and thicknesses of blanks we use here, how does the thickness of a blank affect the frequency?
The resonant frequency of a crystal blank is inversely proportionate to its thickness. Therefore, the thinner the blank, the higher the frequency. The final frequency is controlled during the manufacturing process. In the case of larger blanks, by producing the blank over frequency, and then the final frequency is achieved by adding mass in a process called deposition during a tuning process. In the case of smaller blanks, material is removed using a laser in a similar process.
So on each of these blanks, we have an electrode fitted. What impact does this have on frequency?
So the electrode will add mass to the crystal blank and thus lower its resonant frequency. The electrode is attached using evaporated silver in a process called deposition. The electrode thickness is accurately controlled, and the resultant frequency shift can be accounted for. Therefore, the required frequency of the finished crystal can be achieved.
So with a diverse range of sizes we have here, like you do on different packages, how do we limit the sizes of blanks?
The smallest size crystal we produce is 1.2 by 1 millimeter. However, it's worth mentioning that due to the very small size of the blank, the frequencies available will be lower, typically only up to 80 megahertz, as the crystal needs to be thicker in order to be processed and mounted in such a small package.
So the shape of the blanks seem to be standardized. Why are blanks always rectangular or circular?
The shape of the crystal blank is primarily due to the enclosure that the blank is designed to fit inside. For a standard AT-cut crystal, the active area of the crystal is between the electrodes, bonded to either side of the blank. There needs to be enough material surrounding the electrodes to dissipate any acoustic waves. Otherwise, we will get reflections, and this will cause unwanted vibrational modes and noise that may be detrimental to the crystal's performance. The best shape for a crystal blank is a circle, as the acoustic waves will propagate from the center and always hit a perpendicular wall on the outer edge of the crystal. However, due to crystal miniaturization, this shape of blank is not feasible, and so the blank has to be rectangular. Fortunately, due to advances in oscillator driving circuits, it's possible to drive these crystals at a very low drive level, so any acoustic waves are dissipated before they reach the edge of the blank.
So when we talk about temperature ranges for oscillators, how does the temperature affect the frequency?
The cut angle of the wafer from the crystal bar defines what kind of temperature response characteristics the crystal will have when used in an electronic circuit. The temperature response curve is known for all cuts of crystal. For AT cut crystals, for example, it is dependent on the deviation from the standard cut angle of 35 degrees 15 minutes with respect to the z-axis of the crystal bar. An AT cut crystal of any frequency will follow this curve. Watch crystals follow an inverted parabola temperature coefficient. This too is a known constant, and thus frequency deviations due to temperature variation can be accurately predicted.
So a product range from low kilohertz up to hundreds of megahertz. Are there limits on the frequency range we can produce?
Modern surface mount AT cut crystals usually aren't produced with a resonant frequency lower than about 8 MHz. This is due to the physical size of the crystal blank, as lower frequency crystals are much thicker than higher frequencies. As this graph shows, the crystal size is reduced, the lowest available frequency for that package size is increased. Older, larger packages have enough space to accommodate larger, thicker crystals, so low frequency crystals are available, but may not be suitable if the PCB real estate is low, thus requiring a smaller crystal. Fundamental mode AT cut crystals typically top out at around 200 MHz. Frequencies beyond this are possible, but due to the blank being very thin, these are harder to produce and control. Special processes have been developed to produce these higher frequency fundamental mode crystals. For example, a plasma etching technique that's designed to remove material from the center of the crystal, but leave a thicker rim in order for the crystal to be mounted and add additional strength. And the center of this crystal blank could be between 25 to 50 microns thick. As these processes are specialized, the cost of these types of crystals is increased. Another method of producing higher frequency crystals is to take advantage of harmonic frequencies. Harmonics, as in music, are notes or frequencies 1 octave higher than the root note or fundamental. These harmonics occur naturally and are multiples of the fundamental frequency. We call these harmonics overtones. Overtone crystals operate at either the third, fifth, or seventh multiple of the fundamental. The oscillator circuit is specially designed to operate in these modes by using a high-pass filter to block lower harmonic modes. Higher frequency crystals are typically produced in this way, but in general, they will still be within the megahertz range.
So in the initial training here and for the last 6 months, we speak a lot about the importance of picofarads on frequency. What influence does picofarad have?
The picofarad load, or the CL value, for a crystal resonator is required in order for the crystal to resonate at the correct frequency. If the CL value is different from the specified CL value, the crystal will not resonate at the specified frequency, and in extreme cases may not function at all. The CL value on the datasheet has to be translated into the physical values of the onboard capacitors of CA and CB, using the formula CL equals CA times CB over CA plus CB plus CS, where CL equals the capacitive load and CS is the capacitive stray caused by tracks or traces, typically between 2 to 7 picofarads. However, because you can only estimate the stray capacitance, it's really important to measure the frequency of your actual circuit to recheck that the frequency reaches the required accuracy for your application. To find the required values of CA and CB, use the transposed formula CA and CB equals 2 times CL minus CS. It is assumed that CA and CB are equal. If, however, CA and CB cannot be equal due to standard component values, then CA should be a smaller value than CB. The pullability or the trim sensitivity to changes in CL are measured and recorded here at IQD. These values are expressed in parts per million per picofarad change. It is important to note that this value is not linear and is only representative of the trim sensitivity around the CL value. Additionally, crystals with a lower CL value tend to be more sensitive to changes in load and therefore have a higher trim sensitivity value.
So when starting, it was quite obvious there's one particular crystal which is a completely different shape to the others. Why are watch crystals fork-shaped?
Most watch crystals are designed to resonate at 32.768 kHz. This frequency is special because when the output is passed through 15 SR latches, or the frequency is divided by 2 15 times, you'll get a 1 Hz tick. Additionally, frequencies above around 20 kHz are not perceivable to the human ear, so you'll not get an audible tone from the watch or clock. Due to the relatively low frequency requirements of watch oscillator circuits, a standard AT cut crystal would not be suitable, as the resonant frequency is inversely proportionate to the blank thickness, and the crystal would therefore be far too thick to fit inside a standard enclosure. Watch crystals operate in the flexure vibration mode. The working principle is the same as of a metal tuning fork. The two tips will vibrate at a certain frequency. This frequency is defined not only by the mass of the tips, but is related to the mechanical dimensioning of the tuning fork tips, which includes all 3 dimensions, the length, the width, and the height. Additionally, due to the very high ESR of the particular cut of crystal, this results in a very low drive level. This is important as these crystals are used in watches and clocks, powered by a small coin cell, which is designed to operate for years.
So is there any circumstances which can damage or crack the crystal blank?
The crystal blank, or the mounting structure, may become damaged if subjected to physical shock and vibration. However, they should not suffer damage if they are not subjected to shock or vibration outside of that which is stated on the datasheet. You can also damage a crystal electronically by overdriving it. You are unlikely to damage the crystal itself in this way, but may degrade the quality of the crystal mounting structure, thus degrading the crystal's performance.
So for every quote or inquiry we have here at IQD, we check the date of manufacture of all our crystals. Why do we need to retest after 24 months?
IQD's products are designed and manufactured to provide many years of reliable performance in customers' circuits. The vast majority of our products are delivered to customers within 2 years of manufacture. However, on the rare occasions that we do not ship products that were manufactured in the last 2 years, the products will have been stored in an appropriate environment, solderability tested, and are still covered by IQD's normal guarantee. Supported by the evidence of 40+ years experience that quartz-based frequency products suffer no detrimental effects in performance from an extended shelf life. Customers need not have any concerns about accepting such products, in line with the recommendations of other leading component manufacturers. For further information on this, please do not hesitate to contact myself or Malcolm, who can assist further.
So an oscillator has a circuit built in to generate a set frequency. What is included in this package?
So an oscillator is an integrated circuit, or IC, that has a crystal resonator, a Pierce oscillator circuit, and an output stage built in. All you have to do is apply a voltage and you will get the correct output frequency. Oscillators come in many different varieties and offer many stability specifications or control options by using different technologies. For example, a temperature compensated crystal oscillator, or TCXO, where the crystal's typical response curve over temperature is compensated for, or a VCXO, or voltage controlled crystal oscillator, that has a voltage control input pin, allowing for fine adjustments of the output frequency using an analog voltage. The oscillator output can also come in many recognized standards. For example, CMOS, sine, LVDS, LVPECL, and HCSL. Additionally, the oscillator IC may have a chip enable or tri-state function input for low power applications.
So you mentioned voltage controlled crystal oscillators. How does the voltage affect?
A voltage controlled crystal oscillator uses varactors or varicaps to slightly change the value of the load capacitance proportionately dependent on the applied control voltage. This results in a change in the output frequency of the oscillator, typically plus minus 50 parts per million to plus minus 150 parts per million across the input control voltage range.
So we have a wide range of oven-controlled crystal oscillators within our product. One has a disciplined version. Why do we need disciplined OCXOs?
An oven-controlled crystal oscillator removes the effects of external environmental temperature changes by keeping the crystal at a stable temperature above the intended operating temperature range, typically between 90 to 95 degrees C. This temperature is kept very stable by a thermistor feedback circuit mounted directly on the crystal can. The thermistor is an infinitely variable analog device, meaning that the current that is allowed to flow through the heater coil can be very accurately controlled. This whole assembly is housed in a well-insulated oven. The main objective of this assembly is to get the temperature sensor, heater, and crystal to all be in as close thermal proximity to each other as possible to minimize the hysteresis or the thermal lag. The temperature of the crystal is maintained to within 0.1 degrees C of the inflection point of an SC cut crystal of around 92.5 degrees C. This will vary slightly with every crystal, and so the OCXO oven temperature is hand-tuned to match, thus keeping the crystal at the flattest point on its respective curve. A disciplined OCXO goes one step further to this by incorporating an advanced adaptive algorithm that, when coupled with a known 1 Hz clock signal, can be trained to tune the output even further. Thus, over time, is capable of producing an output that, when the reference is removed, will not wander for more than 1.5 microseconds for up to 24 hours with respect to its reference clock. To give some context, 1.5 microseconds is about the same time as a camera flash.
So we've reached our last question on our most complicated product, but probably the most interesting. What are rubidium oscillators used for?
A rubidium oscillator is a type of atomic clock. They typically use a voltage-controlled OCXO to produce the output frequency, but this output frequency is in turn locked to the hyperfine transition frequency of a glass cell containing rubidium vapor and a lamp, known as a physics package. The OCXO output is taken and then multiplied up to around 6.835 gigahertz via a VCO or RF synthesizer. The cell is then exposed to this microwave frequency, and this in turn causes the rubidium vapor to change quantum state. This transition in quantum state, known as a hyperfine sublevel, is detected and fed back into the OCXO voltage control input in a closed loop. Any deviation from the hyperfine transition frequency will cause the voltage control input to change, thus pulling the OCXO back on frequency. In this way, a frequency stability of 5 parts per trillion is achievable. Rubidium oscillators are used as standalone frequency standards for laboratories and high-precision test equipment, as well as fallback for telecommunications and broadcast equipment when the primary sync source fails.
Thank you very much for your time today. I hope you found the presentation helpful. Chris and I will take a few questions now, but if you have any questions in the future, you need clarification on any of our product, please reach out to your local Würth Elektronik ADM or contact us directly on the information on screen now. Again, a big thank you for listening today, and hopefully we can meet you face to face in the not too distant future when things improve, hopefully. I'll hand it back across to Marcus now for the questions, and again, thank you very much for your time, everyone.
Yeah, thank you. Yeah, thank you to both of you, Malcolm and Chris, for your nice and interesting presentation, at least from my side. I found it very interesting, good questions. Yeah, as you have mentioned it, now we would like to turn our attention to your questions, and so we wait a little until some questions come in. But yeah, I can see there were also some questions in the meantime coming up. So yeah, then let's just start into the questions. So first question, what are the advantages in using quartz frequency products over other technologies, for example, MEMS?
Okay, it's a very good question. So quartz resonators naturally have a very high Q factor when you compare to MEMS and other frequency products like ceramic resonators. Also, quartz crystals tend to have a very good stability when you compare to ceramic resonators and MEMS. On paper, MEMS and quartz oscillators are similar, but MEMS tend to suffer from frequency jumps, whereas quartz oscillators tend to have a more linear frequency response across temperature ranges. Also, MEMS devices have a higher component count because they need external phase lock loops and temperature compensation circuitry to function. So therefore have a higher current draw as well as complexity when designing circuits. But that's not to say that MEMS and ceramic resonators don't have their place in the market, because they are more resilient to shock and vibration typically than quartz devices. And they also may be a more cost-effective option if high stability and good phase noise and jitter performance isn't a priority.
Okay, Chris, thank you very much for your explanation. Then let's go on with the next question. So, are there any tricks to consider if the crystal has to operate in a non-destructive environment? Like, I think our attendee also added vibration.
I mean, I think for that question is we probably need, need more information about the application. So we've got the whole engineering team and application team here specifically to help customers with questions they got. So I guess as an accountant manager and a salesman, my answer that would be contact us and we'll help.
Okay. Yeah. So thank you very much. Then let's go on with the next question. Except for rubidium clocks, what other atomic clock technologies are there?
So yeah, we've talked about rubidium clocks. There are also cesium atomic clocks. Cesium clocks use a stream of cesium ions that are exposed to a microwave frequency in order to trigger the hyperfine transition. And you've also got hydrogen maser atomic clocks and also optical clocks, which are the next generation of atomic clocks, which are currently being worked on. These use mode lock lasers in order to trigger the hyperfine transition in strontium atoms. This is exciting research, as this will lead to the SI unit of the second being redefined, which is currently defined as the hyperfine transition frequency of the cesium atom. Optical clocks will have hundreds of times greater resolution than the current generation of cesium clocks.
Okay, Chris, thank you again for your explanation. Then, yeah, let's go on with the next question. So, can you say something about aging of crystals and a typical reason of malfunction?
I can talk about aging. So aging is brought about by the materials used in mounting the crystal. It's more about the outgassing of the actual mounting structure. Aging affects the crystal more in the first year, less in the second year, less in the third year, which is.
So it improves over time.
It improves over time, yeah. I can't really comment on the malfunctioning. I think we need more information on that. So maybe contact us directly and we can assist on that further.
Yeah, also there the hint from my side. So if we can't answer your question in the live webinar now, we will answer it later on via email. So you will get your answer. And also if you have any questions left after the session, just email us at exhibition@we-online.com. Okay, then let's go on with the next question. How to select a driver level? The higher, the better?
So the drive level, as long as the drive level is within the drive level stated on the data sheet, it should be fine. It's not really a case of the higher the better. As long as it falls within what's allowed by the crystal, you should be okay.
Okay, thank you very much.
Select something that's sort of in the middle, maybe.
Okay, yeah, then let's go on. Do you provide fit values for the oscillators?
I mean, again, I think if the customer came directly to us, we have the engineering team, the applications team down to understand the application and the ranges required, and we can advise and we can test. I mean, we've got test facilities downstairs. So for customers using the oscillator under certain environments, we can replicate that downstairs here in our lab in Crewkern. And we can actually prove the answer instead of just taking it off the data sheet.
Okay, so thank you very much. Then I think I see the last question for now. Can crystal miniaturization continue, or have we hit the physical limit of what is possible with the current processes?
So I think that the limit has probably been reached for what is possible from a manufacturing point of view and also from what is commercially viable. Crystal blanks less than 1 millimeter are very difficult to produce, as the crystal blank has to be manufactured and mounted. Further miniaturization is possible using microprocessor fabrication technologies, but smaller crystals will have smaller frequency ranges, as we saw in the presentation. So in developing even smaller crystals, you will limit the market potential for such devices.
But science moves on so quickly, who knows?
Yeah, that's right. Okay, so thank you very much, both of you, for your interesting presentation today. And yeah, now we are finished with the presentation. If there are any questions left now, we will answer them later on via email. And of course, you can just email us at our shown email addresses. So thank you very much for your attention, and I hope you enjoyed our presentation. Also, just a hint, I will just share my screen. Yeah, because today it goes on with our digital days and our virtual conference with the next session and the next topic, transformer design for EMC, practical construction techniques. So it will start tomorrow at 9 a.m. European Central Time. So yeah, don't hesitate and come in. So thank you very much again. See you there, and I hope you enjoy our digital days. Goodbye.
Thank you.
Thank you.